Hi, welcome to Chapter 9 and Chapter 12, Molecular Orbital Theory and Band Gap, Part 2, where today we're going to talk about Chapter 12, really, band gaps. So why do we need the molecular orbital approach for metals? Well, we've always talked about this electron C model, where the electrons are not attached to any particular atom, so they're free to move around, so they're delocalized. And this really explains most of the properties of metals, but it does not explain the trend with melting point as you go across a group. As you go across a group, as you would expect, the more electrons you get, the higher the melting point, the stronger the bonds between the metals. But then you reach this maximum, and then it starts to decrease as you add more electrons. And your electron C model does not really account for that because it just says that you have increased attraction for every electron that you're added. So if that was true, this should continue to go up and not come back down. But if you look at your molecular orbital diagrams, this actually explains why the melting point kind of has this maximum in the middle and then starts to decrease. Because you're actually starting to form some antibonds as you're adding more valence electrons. So let's just review again the rules of molecular orbital theory. Your atomic orbitals combine to make molecular orbitals that extend over the entire molecules. So molecular orbitals are the entire molecules. Atomic orbitals are just around one atom. A molecular orbital can have 0, 1, or 2 electrons in it. The number of your molecular orbitals equals the number of atomic orbitals that are combining to form these molecular orbitals. So, if you combined the 1s from one hydrogen and the 1s from another hydrogen, you are combining 2 atomic orbitals, so you're going to form 2 molecular orbitals. What are they? In this case, it would be sigma 1s and sigma 1s star for the antibonding. So you form 2 molecular orbitals because you combine 2 atomic orbitals. Adding electrons to a bonding molecular orbital will strengthen the bonding, while if you're adding electrons to an anti-bonding molecular orbital, it will weaken the bond. So again, these were the molecular orbital diagrams that we talked about in our last video. Recall that atomic orbitals can combine linearly to build these molecular orbitals. You start your low energy first and you work your way up. And this can lead to bonding, anti-bonding, and some non-bonding orbitals where nothing is in them. So let's talk about the band theory. So when we were talking about molecular orbitals, we were mainly talking about diatomic molecules, just 2 atoms, what happens when they come together. But what happens when you start adding more and more than just 2 atoms? Well, then you tend to get too many of these molecular orbitals to draw. So what they do is they just kind of make this rectangle here, and they call this a band that kind of covers, this blue band covers all the bonding. So this is your bonding orbitals. And the pink band here covers all of your anti-bonding. So it's just an easier way to represent it as these bands. But no, inside these bands you do have your molecular orbitals. So in this case, here we're only talking about our s orbitals because we're talking about hydrogen. So in theory, this is, if you had a chain of hydrogens, you would have these bands. When we start talking about metals, remember metals have d and p orbitals that you need to consider. So their band diagrams or molecular diagrams are a little bit more complicated. And I just wanted you to see this. You don't have to actually understand it, but just see it that it is more complicated. But again, what they're doing is they draw this line here where the bottom part are your bonding molecular orbitals and your top are your anti-bonding. So let's take a look at this. For metals, your bonding, so the bottom of the blue one is the bonding. Molecular orbitals. And the top one is your anti-bonding. These bands are touching each other, okay? And when we're talking about these bands and band gap theory, they rename them, the bottom one, as the valence band. Remember, when you're forming bonds, what electrons are being bonded? The valence electrons. So that is why this bottom one, that is your bonding molecular orbital, is called your valence band. Up here are your anti-bonding. So here you have electrons that are not bonded. They are free to move around. If they are free to move around because they're not held to one particular atom, they're going to conduct. And that is why this top band here is called your conduction band. Now notice what's happening as we go. So this is for metals. The two are touching. So it's very easy for an electron to jump up to here and then conduct. And that is why metals are very good conductors. Then we move to our semiconductors, where the band are not touching each other. There's a gap in between. And this gap in between is called your band gap. So now it's a little bit harder to get an electron to jump up here and conduct, because it has to jump over this band gap, which has a specific energy. And here's your semiconductors. And that is why sometimes they conduct and sometimes they don't. Because if you have enough energy, it could jump up to here and conduct. If you don't have enough energy, it'll stay down in the valence band and it won't conduct. And the last type of material we have is our insulator. And look at, this is a very large band gap. So large that your electron cannot jump up into the conduction band. And that is why they are insulators. You can't get the electrons to go up here and conduct. Okay, so in order to conduct electricity, you need to take your electrons and promote them from the filled valence band into the empty conduction band so that they can move around. So here we again have our same diagram that we saw on the previous slide. And here in metals, they are good conductors. So they have a very non-existent band gap or a very small band gap. They are basically touching, so it's easy. Next to no energy is needed to get them to conduct electricity. So this is why it is quite easy for the electrons to be promoted or jump into the conduction band and conduct electricity. Now your semiconductors, which happen to be the most important kind of conductors, they are used in most of your electronic devices. Their band gap is small enough that you can promote an electron, but it's also large enough that it takes some energy to get there. So you can control, and that's what they do. By picking the material that you're making your semiconductor out of, you could control this distance. If you want it to conduct more, you'd want the two to be close together. If you want it to conduct less, you want them to be further apart. And then finally, your insulators, the band gap is very large, so it makes it very difficult, next to so much difficult that most of the time it's not going to happen. You're not going to get your electrons to go up here and conduct, so that's why they are called insulators. They do not conduct. So how can we adjust our band gap energy? Well, the band gap energy depends on a couple things. First of all, it depends on how well your orbits are overlapping. The greater that they are overlapping, so look at this picture here. Here's your overlap area. And look at this picture here. Here's your overlap area. This one is overlapping more. So what is happening to the size of your band gap, the more that the orbitals overlap. So the greater the overlap, the larger the band gap. So if you want to make a material so that it has a large band gap, you want to make sure that the molecular orbits are overlapping quite a bit. Over here, they're not overlapping quite as much, and you notice the band gap is much smaller. So again, the greater the overlap of your molecular orbits, the larger your band gap. Polarity also influences your band gap. So the greater the electronegative difference, which basically means the more polar your material is, the larger the band gap will be. So the greater the electronegativity difference, the larger the band gap. So here is just one element. So you would look, so it's not, since it's just one, it's not polar, and this is the size of your band gap. But then if you take two and you subtract electronegativity differences, it's going to be a little bit more polar, so you'll have a larger band gap. Because think about it, as you increase polarity, you go from being a nonpolar covalent to a polar covalent, And then if you continue to increase polarity, what do you become? You become an ionic compound, right? And ionic compounds are most of your insulators. So here's some properties of materials. So you see here you have your insulators, then you have your semiconductors, and then you have your metals. If you look at your band gap energy, the insulators have the highest, the semiconductors are kind of in the middle, and the band gap energy for metals is almost non-existent here. So semiconductors, they have this gap between the valence band, which is your bonding molecular orbitals, and the conduction band, which is your antibonding. Okay? So your electrons must enter the conduction band for the electrons to transfer. Okay, most of your semiconductors will have a band gap range from like fairly small, 0.08, to around 3. If you exceed 3.5, then that's considered an insulator. So what forms a semiconductor? Well, most of the time it is your group 4A elements, because you want 4 valence electrons. That is key there. So most of your semiconductors, you want 4 valence electrons. So if you look here, here is your group 4A. So you have silicon with 4 valence electrons, germanium, and it's one of the tins. It's called gray tin that will form a semiconductor. Then you could also combine elements to make semiconductors. But when you combine them, the average of your valence electrons should be 4. So take gallium and AS. Gallium has a valence of 3 and AS has a valence of 5. So when you add them together, take the average is 4. So 4 is your magic number for your semiconductors. So there are 2 types of semiconductors. One that is just pure element, and they're called elemental semiconductors, and that is 1 atom, and that is your group 4A elements, okay? So that would be your Si, your germanium, your tin, and we're excluding lead. Lead does not form a semiconductor. As you move down your group 4A, the bonding distance increases, because your atom is getting larger, right? So if the bonding distance is increasing, then you have a decrease in overlap of your orbitals. So if you have a decrease overlap of molecular orbitals, so if that is happening, that reduces the energy difference between the top and bottom bands. So if you're reducing the energy difference between your top and bottom bands, your band gap is decreasing. So as you go down, so remember, just in case you forget what band gap is, this is the band gap. As you go down a group or family, this distance here is decreasing. So they're getting closer together. Okay? So the trend is your band gap will decrease as you move down the group 4. And here is some band gap energy. So diamond, which is considered an insulator, has 5.5 electron volts. That's a form of measuring energy. Silicon has 1.14, so you see it's decreasing. Germanium is 0.67, and then gray tin is 0.08. You're getting closer and closer together, so it actually is easier to conduct as you go down the group. The other type of semiconductor you have is called a compound semiconductor, where you're mixing 2 or more different elements. But remember, your average valence has to be 4. So here are some important trends that occur with your compound semiconductors. Your band gap, so the spacing between the 2 bands, will increase as the difference in group number increases. So the further apart they are on the periodic table, the band gap will increase. Your band gap will increase as a difference in electronegativity increases, which kind of corresponds to this group number, because the further apart you are on the periodic table, the greater your difference in your electronegativity, which also relates to the third one. The band gap will increase as you become more polar. If you have higher electronegativity differences, you're more polar. So how do we adjust the band gap to be what we want? So there's something called doping, where you're just adding an impurity. And you're picking what you're adding so that you can control the size of your band gap. Changing the conductivity of a semiconductor by adding an impurity to an element is what doping is. And you could do it in two ways. You could give it more electrons or less electrons. Okay? So there's two types of doping. N-type is when you're giving it more electrons. More electrons. So the negative charges travel in the conductance band. I spelled this wrong. Conduction. Actually, I had it almost right. Let me just erase that. So the N-type, how do you remember what the N-type means? Well, the N here signifies negative. And when are you negative? When you have more electrons. So more electrons gives you a negative and N-type semiconductor. And if you look here, if you have more electrons, you've now filled your whole valence band, and now you have some up here. You're starting to fill your antibonding. The more electrons you have, right, you're going to fill all the bottom bonding ones first and then move into your antibonding ones. The second type of dopant is called a p-type semiconductor, where you're adding an element that has fewer electrons. So less than 4 electrons. So that will develop holes, what we call holes in the, so if you see here now, the pink is here. So now it's like you have less electrons down here. You have just empty spots, these holes where the electrons would have been. That's called a p-type because if you have less electrons, it's almost like you're becoming more positive. So P for positive holes. So your N-type semiconductors result from adding a pentavalent. Boy, that's some word. Penta means 5, valent. So that just means an element that has a valence of 5. Since 5 is greater than 4, which is what most of your semiconductors have, a valence of 4, this means you have extra electrons. So if you're adding extra electrons, you're more negative, and that is your N-type. And that would be shown right here. Here is another diagram. So antimony, Sb, it's in group 5. It has 5 valence electrons. So you have this extra electron because the Sb will take the spot of where Si was, and Si has 4 valence electrons. Now this one has 5. This extra electron can move up into the conduction band. Okay, the second type is p-type, where you're going to dope it with a trivalent. So an element that has a valence of 3, which is less than 4. So now you're going to have less electrons, so that's why P for positive, and you're going to develop holes. And here's a diagram here. Boron only has 3, and it's replacing a silicon which had 4. So now you have 1 less electron, so here's your hole right here. Okay. Now, when you bring a P and N-type semiconductor close together to each other, you form this junction of an N and P-type semiconductor. And that is how they make diodes, transistors, and solar cells. So LEDs, that you probably are familiar with, is when you combine a N and P-type semiconductor close together. That allows the electrons to move from one to the other very easily. So here is the application of that. Bringing your N and P type together will form what we call solid-state lighting. And if you look at the light bulbs of today, they look way different than Thomas Edison's light bulb, okay? Thomas Edison's light bulb has a filament in it made of tungsten, and you're heating it up. Not only does it give off light, but it also gets very hot. If you've ever touched a light bulb that's been on for a while, you'll burn your fingers. But by using the solid state lighting, these types of lights are called cool lights because they do not get very hot. And they use these semiconductors. And how does it actually work? So if you look here, down here, you have your P-type, which has the holes. So they drew these empty spots as holes. And then up here you have your N-type, which has the extra electrons. And so here you have an external voltage that will push the electrons from the N-type. So here's your N. It'll push the electrons into the holes of the P-type. See, the electrons going into the holes. The electrons fall into the empty holes, and photons are emitted. So you apply a current. So when you're using these light bulbs, you still have to turn on the switch and apply electricity. That electricity makes this electron go into the hole. When it does that, these holes are at lower energy than the electron originally was. So the extra energy gets released as a photon, and that's how it generates light. So your solid-state lighting is a type of lighting that uses semiconductor light-emitting diodes, LEDs. Or you could use organic light-emitting diodes, OLEDs. Or polymer light-emitting diodes, PLEDs, as a source of illumination rather than filaments. These are really taking over the light bulb industry. So let's see if we can predict which of these semiconductors has a larger band gap. So let's take the first one, IN and P. And then we have IN and AS. Now remember our trends. The greater the distance between the groups, but they're really, the distance between the groups is the same here. Okay, the greater the difference in electronegativity. Well, since P is higher, it has a higher electronegativity value than AS. So INP will have a greater difference in electronegativity, so it will have a higher band gap. Okay, now let's do the second one. So we have germanium and aluminum phosphide. Okay. Now, germanium, because it's just pure germanium, you really can't discuss its electronegativity, but because these two are kind of separate from each other, they have a greater electronegativity, and they are more polar than just pure germanium. So, ALP will have a higher or larger band gap. Okay, the last one, let's do it in green. We have silver iodine and cadmium celerium. So this is dealing on the trend that the further apart they are, the larger the band gap. So which two are further apart? Silver iodine will have the larger band gap. And that is the end of our band gap